Hello Math Application students, and welcome to your online lesson. Today we'll be starting a unit on binomial distributions. For our learning intentions, we will learn to define and identify binomial distributions and solve binomial distribution problems using technology on our TI-84 calculators. We'll know we're successful when we can successfully identify why a problem is binomial and calculate its probabilities. So the first question is, what is a binomial distribution? So a binomial distribution is any sort of situation or experiment where the outcome is essentially success or failure. So this might be checking whether something works or doesn't work. If you're playing a game, do you get the number that you want or do you not get the number that you want? Did you pass the test or did you not pass the test? Again, anything that we can talk about, whether you had a success for that thing or a failure, essentially two options, that's what a binomial distribution is. And that, again, that success and failure can manifest in a bunch of different ways, like those examples that I just showed or mentioned. For all binomial distributions, the probability distribution is discrete, and what we mean by that is each trial and each different outcome is something that is a whole number, like it happened or it didn't happen. There's no like half attempt or partial attempt. And if you think back to a unit on statistics, again, discrete means that it is counted. It's not measured, so it's not like a height or a weight. It's a frequency. Did it happen or did it not? Also, for all binomial distributions, as we said before, there are two outcomes, and again, we can usually refer to those as the success or the failure, the thing that we're looking for, or basically anything else would be the failure. And then finally, the trials are independent, and what that means is that each time we do another trial in the experiment, what happened previously has no effect on what's going to happen in the future. So when we talk about binomial distributions, there are some important variables that relate to some important terms regarding a binomial distribution, and we're going to look at some of those right now. So starting with a capital letter X, and this could be a different capital letter, but usually it's a capital letter X. We see this in other probability distributions like normal distributions as well, but X, when it's capital and dealing with a probability distribution, is not a numerical variable. It's actually a variable representing an event, or it's a phrase. It's read in words. So again, anytime we see an X variable, know that that is actual words, and you can often just read that, as we show in the quotes here, that that is the number of successes. All right, and we'll see an example of that later on. But again, a big X is words. It's not a number. And again, it's referring back to your variable, the successes that we're going to have with that variable. P is the probability of successes. So whenever you see P, it's a probability, so again, a number between 0 and 1, and it would be talking about how likely it is to have a success on a single trial. Q is the complement of P, and so P plus Q would have to add up to 1. If you take 1 minus your P, as we see here, that would tell us the probability of failure. All right, so probability of getting the thing that we don't want. R is our number of successes, meaning if I want to do a bunch of trials and I want to make sure at least 3 of them I have a success. So maybe that's 3 times I pass the test, or 3 times that I have a non-faulty product, or 3 times that I roll a 6 on a die. That is the number that we're looking for there. In those examples, that would be 3. And then N is our total number of trials. And so if I do the trial 20 times, N would be 20, and then R is the number of successes I have out of those 20 trials. Another way to indicate important information from a binomial distribution, or to sort of summarize that important information, is to use something often referred to as bin notation. And so this right here is our bin notation, and that shows us that X, which is our distribution, our number of successes, the thing we're talking about, and then we've got this sort of similar symbol here, bin NP. So it lets us know that our variable that we have here represented with our X is a binomial distribution, that's what the bin is letting us know, and that it has a certain number of trials, N, and then the probability of success, P. It doesn't give you details on a specific question, but it summarizes the probability distribution. Again, letting us know it's a binomial distribution, how many trials, and our probability of success for any one of those trials. So what we're going to start with now is actually looking at an example of a binomial distribution problem, much like we'll see in class. And then we'll take a look at this and try to bring some of those things we saw in the previous slides into light with this particular problem. So it says 72% of union members are in favor of a certain change to their conditions of employment. A random sample of 5 members is taken. Find the probability that 3 members are in favor of the change in conditions. So we've seen a few numbers here. We see our initial percent. We see that we have 5 members are being sampled, and then we want 3 of those members to be in favor of our change. So what we're going to do is we're going to go through those variables that we identified in the previous slide and then look at specifics for this particular problem. So big X is the first one we have here, and we already mentioned that big X is a phrase or words. It talks about the thing that we're trying to find the success of. And what are we trying to find the success of? We're trying to find out those who are members in favor of a certain change. So right here, what I just circled, that is essentially our big X. It is the variable, the thing that we're talking about, a statistical variable. So X represents the members in favor of a change. And then P is our probability, and we see that right at the very beginning here. We have our 72%, and that is the probability that someone is in favor of that change. So that's our P, our probability of success. Our Q would be the complement of that. So if we take our 1 minus the 0.72, we end up with 0.28, and that would be the value for Q, the probability of failure, someone not being in favor of that change. R is the number that we want to have be successful, and we can see that over here we said 3 members is what we're looking for. Find the probability that 3 members are in favor of the change in conditions. So R would be 3. And then lastly, N is the total number of trials. And we can see earlier that, again, there were 5 members getting sampled or surveyed in this particular experiment. And so N would equal 5. The next thing we want to look at with this problem is talking about our bin notation. So we do know this is a binomial distribution because they're either in favor of the change or they're not, right? So it's one or the other, success versus failure. And so we can say that our big X is a binomial distribution, and the 2 things that we'd want to have again are the number of trials, which we know is 5, our N value, and then also our probability of success, which is our 0.72. So for our bin notation, we would see that. X is a binomial distribution with 5 trials and a 72% or 0.72 probability of success. And then the last thing we're going to do with this one is I want to look at what this actual question is asking us. So this particular question is asking us to find the probability that 3 members are in favor of the changing conditions. Now, we already know that the probability on any, if I just pick one random person, they have a 72% chance of being in favor of it. That's our P, our probability of success. But if I do this experiment 5 times, what's the probability that I'm going to get exactly 3 of those 5 people who say yes? Again, if I pick one, I know it's more likely to occur than not, because again, this probability that we have of success here, this 0.72, is more than half. But if I do an experiment with 5 trials, what's the probability of 3 of those being in favor? So the way we could write that is we're going to use a big P for probability, and then we want X, which again is the members in favor of change, right? That's what big X is. So if we look down here at our big X, that again is the words. The members in favor of a change is 3. And that's what this question was asking us. We wanted those 3 members to be in favor of change. So what's the probability that the members in favor of change is a total of 3 people? And that's how we would read that, and that's how we'd set that up, and we could even use that to label our answers in the end. So now let's actually do this math. So the exact same problem. 72% of union members are in favor of a certain change to their conditions of employment. A random sample of 5 members is taken. Find the probability that 3 members are in favor of this change in condition. So Again, we can write this out. This lets us know what we're looking for. We're trying to find the probability that the members in favor of the change is 3, that there's 3 members. And we're going to use a function on our calculator known as binom PDF. Anytime we're looking for a specific number of successes, and again, we want 3 successes in this particular problem, we're using binom PDF. So I'm going to pull up my calculator. I am pressing, after I turn it on, I am pressing second. And then going to my vars, just like normal distribution. So second and vars, which is your distribution menu. And we're going to scroll way down past normal CDF and all the things for normal distributions down to binom PDF. If you go a little too far, there's also a binom CDF. For this particular problem, where we just want one value, we want to find the probability of having 3 successes, we're going to use binom PDF. So on this updated operating system, you can see that I can put in my number of trials, my probability of success, my X value, which would be the number that we want, essentially our number of successes, our R, and then finally that'll paste it into the general formula. If you have an older operating system, you would separate these 3 things by commas. So again, our trials we know is 5. Our probability of success is going to be 0.72. And then the number of trials that we want to be successful on, number of successes, would be 3. All right, and so those first 2 things we would get from our bin notation, right? 5 trials, 72% chance of success. And then the second is from the equation that we wrote earlier, right over here, that tells us that our probability, that we're looking for 3 successes. All right, and then I can press enter on the paste. That puts it into the, fills it in just like if we had the older operating system. Hit enter, and it tells us that there is a 29.3% or 0.293 probability of getting exactly 3 members in favor of this change. Again, we used binom PDF for this particular function on the calculator. All right, now we are going to move on to a similar problem. Same setup, still 72% of union members are in favor of this certain change to their conditions of employment. Random sample of 5 is still what we're taking. This time, though, we want to find the probability that at least 3 members are in favor of the change in conditions. And honestly, this question probably makes a little bit more sense, because when it says at least 3, that's referring to 3 or more. So it could be 3, it could be 4, it could be 5. We know it can't be more than 5 because there's only 5 members that are getting surveyed in this particular experiment or study. But we would like 3. So there's a couple ways we could do this. One is we could repeat what we did on the previous slide, where we do the probability of having exactly 3 successes, 3 members, like we just did, and then do the probability of 4, and then also do the probability of 5, and we could add all of those up. So that's one way we could do this. But another way is there's another function on the calculator, and since what we're looking for here is 3 or more, so essentially it's a range of values that we're looking at. But when we're trying to find a range of values in the calculator, we no longer use PDF, we use CDF. So binom CDF. But as you can see here in my notes, when trying to find the probability of obtaining a range of values that are less than or equal to a specific value, we use binom CDF. But you can see here that we're looking for at least 3. That would be that the number of people who are in favor of this change are greater than or equal to 3, as I wrote here. Greater than or equal to 3. Again, 3 or 4 or 5 are what we're looking for. But as I just pointed out, CDF does less than or equal to. So what we could do is we could use the calculator to find out the ones that we don't want and then essentially find the complement or subtract that from 1. So if I want 3, 4, or 5, what don't I want? I don't want anything that's 2 or less. So we can rewrite this as 1 minus the probability of what we don't want. And what we don't want is anything that is less than or equal to 2. That would include 2 people being in favor of the change, or just 1 person, or even 0 people. Those would be those options that we don't want. So let's take a look on the calculator to see how we would do this. So I go back, I press second once again, go to my distribution menu once again, scroll all the way down. You can actually scroll up and it'll get you there a little bit faster. And this time, instead of binom PDF, which focuses on one value, we're doing CDF, which is like a cumulative, adding a bunch of things up. But again, it only does what is less than or equal to, at least with my current operating system, what is less than or equal to the value that we put in. So, number of trials, it's still 5 trials, 5 people are getting surveyed. Probability of success is still 0.72, but this time our x value, we're going to put in the number that we want, that number or less than. And again, since the ones that we want are 3 or greater, we're going to put in the ones that we don't want, which would be 2. That would be 2 or 1 or 0. Anything that is 2 or less is what this function on the calculator is going to do, binom CDF. Paste that in, and we see that we get a probability here of 0.138. But those are the ones I don't want. That's the probability of not getting it. So what I'm going to do is I'm going to do 1 minus, and then on my calculator, I'm going to press second and then answer. And that's going to take that previous answer and subtract it from 1, or do the complement of it, which means there's 86.2%, or 0.862 is the probability that that we would have 3 or more members in favor of the change. And that's what we were initially looking for. So again, by using CDF, we were able to find the stuff that we didn't want and then did a complement. Now, if the question had been different and just literally asked what's the probability that, 3 or fewer members are in favor of the change, then we could have used binom CDF with 3, which would have done anything 3 or less. Here we wanted 3 or more, so we got rid of those that did 2 or less, 2, 1, or 0, and that's what the binom CDF did for us. All right, and that is where we are going to end our lesson for today. Until next time.